Intrusion Detection System, eBPF and Rust. What if I told you that this single Rust program can detect whole scans in real time directly from the Linux kernel with zero packet drop and microsecond latency? So what you see here is a running code that has no user space packet copying, no performance overhead, just pure kernel speed intrusion detection. So in this series, we are going to see how we are going to build an intrusion detection system. So this is going to be of multiple parts, and here we are going to speak about the eBPF technology, the IO framework, and the Rust features that we have used for into it. Traditional IDS versus eBPF IDS. Let's start with a fundamental question. How do traditional intrusion detection systems work and why are they fundamentally limited? Picture this, a packet arrives at your network interface. In traditional setup, the journey looks something like this. First, the kernel copies the packet from the network interface into the kernel memory. Then it processes it through the entire network stack, where it's the IP routing, connection tracking, and firewall takes place. Finally, it copies the packet again into the user space and through a system call where intrusion detection you finally see into an action. This means that a packet gets copied at least twice, and the context switch between the kernel and the user space, and it is processed already after it has been handled by the network stack. For a high speed network, this performance is a nightmare. But there's a bigger problem. Our system has to be very reactive. By this time, the IDS sees your malicious packet, the kernel has already processed it, routed it, and potentially even delivered it to the target. So now let's look at the current scenario where we have the eBPF technology, that's extended Berkeley packet filtering. Despite the name, it's evolved far beyond the packet filtering into a complex kernel programming platform. The game changer here is that eBPF lets you run its custom programs directly inside the Linux kernel, but not just anywhere. It has strategic hook points, which we will be discussing further, where we can intercept and analyze and even modify the system's behavior in real time. For example, I'll just give you like we have something called as XDPs, that is your express data packet. These catch the packets at the network driver level before any kernel processing. Then we have the traffic control, which we have used in an example here. This intercepts the packet after basic passing, but before the routing decision. And we have many more like socket filtering and trace points, K probes, U probes. We'll be discussing more over here. But as we see in our sports scanner detector, here our entire where our right ones. Yeah. So here our entire post scanner detector runs inside the Linux kernel when the packet hits the network interface. Our code simply immediately reacts to it and scans the pattern and makes the decision in microsecond. The another thing is that the direct memory accesses. Here we don't have two copies. We take over here. Generally, here what is happening that we get here something that's really powerful. Traditional user space program receives a copy of the packet. But eBPF here has direct access. As you can see that load is happening over here. So we directly look at the function load isn't copying the data. It gives you a type view directly into the packet memory. So the Ethernet header starts from the offset 0 and the IP header starts from the offset 14. And we are just passing into the network protocol with zero allocation and zero copy. So what happens here that this makes the eBPF tool processing the packet very fast. So it can go at a line rate of up to 10 gigabytes to 25 or even 100 gigabytes packet without dropping any network packets or impacting the system's performance. eBPF VM architecture, the eBPF verifier and the JIT compiler. The question arises here is that we are putting the eBPF code directly into the kernel space. Kernel, that is the heart of the operating system. How can we risk it? So the kernel safety runs our custom code. This is where the eBPF machine comes in. eBPF defines a virtual instruction set. It's like a tiny CPU architecture that is designed for safety and performance. When we compile our Rust code, it gets translated into the eBPF bytecode that runs on the virtual machine. But the crucial part over here is how is the code being verified? That is being verified by the eBPF verifier. The kernel loads a program, it runs into the eBPF verifier, one of the most sophisticated static analysis engine ever built. So the verifier analyzes our program execution path to our program and proves its all the mathematical properties. Here it will check over here for that it does not have our code does not have any infinite loops. When I say infinite loop, that every loop must have a bounded iteration count. The next thing it will check for is the no out of bound memory access. All the memories that are read are validated. No null pointer dereferences. So all the pointers are moved that we are going to access in our kernel code is being verified before being the kernel loaded. And it does not have any undefined behaviors. Like the program is perfectly deterministic and the resource limits respected. So we have whatever your stack usage, your instruction count and memory access, they all are limited. If the verifier, that is our eBPF verifier, cannot prove that our program is safe, it simply refuses to load it. This means that once your eBPF program is loaded, the kernel itself guarantees that it cannot crash into the system. This revolutionary, what we can say, that we can write our kernel code with confidence that our mistakes won't bring down the whole production system or the whole operating system. Aya template creation. All right. Now that we have understood why eBPF is revolutionary for security, let's get our hands dirty. I'm going to show you how to create a complete eBPF project from scratch using the IR template. And trust me, it's way easier than you might think. By this end of the session, you'll have a working eBPF classifier project with proper Rust tooling, and you'll understand how the code is generated from the and organized between the kernel and the user space. So for this, you can go over here to the IR website, and IR provides you the template that generates the entire project for project structure for us. It does not need any complex build systems or configuring the linker script. Haya and handles all this complexity. So over here, when you go, it will specify how to generate the whole process. Here you could, then you have your simple uh, development environment. It will give you all the prerequisites that you require, and you can just actually generate this program using Haya. So here I use cargo generate. So over here, this generator will ask you several questions. So let me take you through each. Like the project name for now, I'm just creating a dummy project. I say dummy project. And then the most important thing is that it gives you choices from which eBPF program you want to do. Today we are doing the program type classifier. So Aya even supports many other program types like the XDPs. That is for ultra high performance in networking. Then you have your LSM for security hooks, trace points for system monitoring. But what we are doing here is the classifier. That's perfect for a intrusion detection system. So I take the classifier, and over here we are taking the ingress. I'll explain you what is egress and ingress, and your project is created. So you can go into cd dummy and then run your program. So this is your dummy code. So here it will be having three spaces. That is your kernel space, the common folder, and your user space. So I'll be explaining you this everything. Classifier. Before we go into the workspace explanation, actually, I would like to first make you all understand what we are building. We are trying to build a traffic control classifier. But what it actually means is that here we have been using classifier, but not HTTPs or socket filtering, LSM hooks, and trace points. Why so? The reason for this is that in the Linux networking stack, the traffic control that is the DC is in the kernel subsystem that manages the network traffic flow. It sits right below the network filtering mechanism where the packets are passed, but it's before the routing decision, before the layer that does the routing decision. So this makes it perfect for security application. A classifier is basically a special type of eBPF program that gets attached to the TC layer, and when a packet arrives, it does the following thing. First, it inspects the packet contents like the headers and footers. It will analyze the pattern and update the statistics. It will make decision about what happens next, and then it drops, redirects, or passes the packet through it. The key advantage here is that we see before the kernel makes the routing decision, so we can catch the attack early and even prevent any malicious attack from happening. For our port scanner detector, the classifier will examine every TCP and UDP packet, track the connection pattern, and alert us when the scanning behavior is detected. So over here, you can see that we could even use the XDP, but that's faster, but it has less context. Socket filtering, that is for your post routing or reactive. LSMs, we basically use for security events, and trace points are for system calls and not packets. eBPF project architecture. We've seen how to create an eBPF project from the IR template, and we have seen what are classifiers. I would like to introduce you to the project directory over here that we have the three-tier architecture. So every IR project follows a three-tier architecture that separates the concerning area cleanly. So first is the root level where the project coordination is maintained over here. So over here you have your cargo log, cargo.toml, your readme, and all the projects over here. So if you check the cargo.toml over here, we mentioned all the members that are part of the project, like your eBPF networking. This is your user space. eBPF networking, eBPF is your kernel space, and eBPF networking common is your common directory where we have all the structures and all which have been commonly shared between the kernel and the user space. So these are all the dependency that we'll be using into the project, and the root like basically defines a workspace. This tells the cargo how to coordinate building multiple related crates together. You could just think of it as the conductor of the whole orchestra. So after that is your this is your user space code, and this is your kernel space code. So the kernel space code is actually where the magic happens. eBPF contains the crate that contains the code that literally runs inside your Linux kernel. So when we are working on the user space, if you notice that we have no standard and no main. So when we have this no standard, we say that we are not going to use any standard libraries like no heap, no file, IO, or threads over there. And when we are saying no main function, we are telling that eBPF has its own main function and we'll be following it over there. Then there are the maps, which I'll be explaining you all in detail. And then this is the classifier. This is where the actual program that is going to be attached to the network interface. So it internally calls the process packet, and where the logic, how the packet has been processed, which will be checking in the next part, is being shown over here. Then here we come back to our user space, where the user space is the program where you're typically it's your typical Rust application, and this is where we have the Tokyo, which I'll be explaining to you all how the async is happening over here. Then you have your memlock, again memlock, and it's the loading and your all the programs, how your eBPF, the kernel level is connected, converted into the bytecode. So we'll be going through all the user space, kernel space programming in detail in the next part over here. This is just a brief overview. So the main thing what the user space is responsible for, it loads the eBPF program into the kernel. It attaches it to the network interface. Then all the reading events and alerts from the, it will read all the events from the kernel space, and then it manages the configuration and the logging process. And the third one is your eBPF common. So here is the, again, this is a brilliant design where it will show you all the structures that have been shared between the user space and your kernel space. So the data transfer is smoothly between them. So this is our complete project over here. So to give you a brief overview, again, I would like to show you a brief again that this is your eBPF program, your BPF map, which is in the shared section, and the user space application, which is in the user space. Your eBPF will see the packet, extract the IP address, port, and all the details. Then it would update structures which are there, like the scan info. It will check the threshold and then send alerts. The map is where the scan key or the scan info, whichever key and value pair, the source IP, it will be storing them, the events queue and scan alert data. And this will be triggered over your in your user space, where it would be reading all the data which has been put in the kernel space. It will process the structures, scan alert, and then raise the notifications to you. Common shared data structure. Now that we've seen the basic architecture where your user space, kernel space, and common folders are there, now let's go into dive into the code itself, where we actually see where the theory meets the reality, and you'll see how elegantly the Rust makes your complex kernel programming easy. So the first one is that we are going to see is the eBPF network common. So this is the common definition file that is the bridge between your kernel space and your user space. So the first thing you see is, again, over here you have the no standard this thing. So you'll notice that it's a no standard. So this is crucial because our shared structure needs to work in both your kernel space and the user space. But in the kernel space, we have no standard libraries. We cannot use a standard library. That's why this forces us to use only core Rust function features over here. So after that, you see that we have three constants that define our, what you say, detection strategy. The first one is your scan window seconds. That is your 60-second time window. Like, we bucket all our activities into this chunk. The next one is your port scan threshold. That is like over here we have said we want 10 unique ports. If we hit more than this, you trigger a scanner alert over here. Then after that is your max scan entries. So we are taking 10,000 max scan entries, which prevents memory exhaustion into the kernel. So after that comes your BPF map key structure. So here, this is actually what you can say is the heart of our tracker. So the scan key is a hash map key, you could call over here. So over here, you can see the scan key stores your source IP and the time bucket. But over here, if you see, we have the recurse C attribute, which is very crucial because it ensures that this structure has the same memory layout in both our kernel space and the user space. Without this, the data corruption is guaranteed. Then you have your clone and the copy trait, which makes the structure copying very easy to duplicate it. So this is essential for your, what you say, all your hash map keys. After that, we come over here is the scan info. So your scan info is actually like what we are going to track per scanner. So this captures the scanner's behavior profile. Notice that we track both the unique port and the total attempts over here. This will help us distinguish between the aggressive scanners and a normal network activity. Then is the scan alert. So scan alert is the structure which alerts are sent from your eBPF to the user space where the scan is detected. This travels again. This is via your perf event array. So the scan alert is when we detect a scan. So this is structure carries the evidence to the user space via your perf event array. But you will notice that everywhere we have something called as unsafe impulse IA pod for scan alert, unsafe impulse IA pod for scan info, and the same for your scan key. So this pod, what we say is the plain old data implementation. So this tells the IA structure that it can be easily transmitted between your kernel space and the user space. And the unsafe keyword reminds us that we are making promises about the memory safety that the Rust can't verify. Kernel space, the eBPF program. For our main event, now let's see our eBPF kernel program. So this is our kernel program main.it. So we are running in the kernel space. So here, as we're running in the kernel space, there is no heap allocation, no standard libraries, no main function. This is just a bare metal Rust programming. This all are the includes that we have dependencies that we have included. Then here comes the main, that is the BPF shared data structures over here. So as you can see, the first one is the scan tracker. This is our main tracking map. This is like our primary data structure. We have used the LRU hash map. When you say the LRU hash map, it's the least recently used hash map. The LRU policy is crucial here because whenever we hit, like you say, 10,000, the max entry, that is your 10,000 entries, the old entries are automatically disappear. So this prevents your memory exhaustion while keeping the recent scanner in memory. Then after that, it's your communication channel to the user space. The perf event array is the eBPF high performance way to send data from the user to data to the user in the user space. Think of it like a lock-free ring buffer optimized for kernel to user space communication. Then is your port duplication map. So again, the port duplication map is your port tracker. This is also the LRU least recently used hash map. So here, the port tracker, I'll show you, we have very, what do you say, cleverly optimized it so that we can use 3 bits, what do you say, data into the 64 bits, which I'll be explaining you the port tracker again. Then comes the main program entry, that is your classifier over here. So the classifier macro tells the IR that this is a traffic control classifier program. Every packet hitting our interface calls this function, and then this function returns either TC at OK or TC at pipe, which will tell the kernel what to do of the packet. This internally calls the process packet. The process packet is where the actual logic, what I say, is of the detection work is going on. So in the step one, what we see over here is that we pass the Ethernet header. So while passing this Ethernet header here, you can see that we are doing a call to CTX load. So here what we are doing is, again, we are doing zero copy packet passing. This means that it reads from the packet buffer in the kernel memory. So here we don't have any, no mem copy, no allocation, just pure performance. After that, we are doing the filtering for our IPv4 packets. That is, like, we only care about the IPv4 packets, and all the other packets, be it your IPv6, ARP, or any other protocols, that those are, all are ignored. Then we pass the IP header. We pass the IP header to get source IP. So here, what you notice that while getting a source IP, we are doing the byte order conversion, because the network packets are usually in the big endians, but most of our CPUs are in the little endian. So this does a conversion from the big endian to little endian. After that, we have your protocol specific port extraction. So we check the packet if it's a TCP packet or what is your UDP packet. So This packet elegantly handles both TCP and UDP, and gracefully it will ignore the other protocols packets like ICMP, etc. After that comes our time, this portion, that is your time bucketing the sliding window. So here what we do is that we are converting nanosecond timestamps to 60-second buckets. So this creates a sliding time window where all the activity within the 60 seconds get into the same bucket ID. After that is the trick which I was telling you. That is your port deduplication trick. So over here, what is it that we are doing is that we are mastering the art of, you say, bit manipulation. Here we have three values, that is your source IP, time bucket, and destination port. Your source IP, which is 32-bit, your 16 IP again, which is your time bucket, which is a 16-bit IP, it's truncated, and your destination port again, which is your 16 bits, which has been truncated, and we pack them into all in the port key, that is your 64-bit. And then we check if this is a new port, if this port was the packet which has come is hitting the same port which was there previously, or it's a new port. If it is a new port, then we just insert the key over here into a hash map. And then it's the moment of truth where the actual scan detection happens. This is the where the existing scanners have been updated over here. So here you see that again that everything is in the unsafe block. So here when we say the unsafe block, again it is necessary because we are doing directly manipulating the memory through a raw pointer. So eBPF cannot provide the rushed normal borrowing guarantees. So again, we have to, whenever we cross the threshold limit, this will be fired. The alert will be fired. But this is again on our risk. So we have to take all the precautions that whatever the dereferencing we are doing is proper over here. And then basically again, we are putting it into the scan info. And then we are inserting it into the scan tracker. User space, control and management. Now that we have seen our common structures into the common library like eBPF, network common, and then the kernel space, it's time to see what our user space program says. So the user space program, the main thing over here is that we are using async rushed with Tokyo. So we are using for the main, we are using the Tokyo crate over here. So why are we using that? We are using this, so we have a async runtime. This enables us for a non-blocking IO and efficient event handling. So that's the reason we're using the Tokyo crate over there. Then we have the command line parser with clap. So this is what the clap provides you a zero boilerplate command line passing. This derives the macro, automatically generates you to validate your text and any other validations over here. So let's dive into the main code over here. So when you see the main code, first thing is that we have the memory limit manipulation. That is the we bump the memory memlock R limit. So the reason to this is that it removes the locked memory limit. So our eBPF program needs to lock the memory pages, and the older kernels have restrictions by default. So we remove that memory and we check if we have successfully removed it. After that, the part that we are going to do is that we need to include our eBPF object file as a raw byte at the compile time and load it at the runtime. So this approach is recommended for most of our real world use cases. But if you would like to specify the eBPF program at the runtime rather than the compile time, we can use the eBPF load file. But for now, we are using the eBPF load functionality. But when you see over here, we have been using include bytes aligned. So this embeds our compiled eBPF bytecode directly into our binary. So no external files are needed for this. And once at this stage is where the eBPF verifier runs and it verifies our kernel code. And if it fails, it would not be inserted over there and you would be getting the message over here. So after this is where the attachment is done to our network interface. So here first you can see is that over here this line over here adds a CLS at QDisk to the interface. Like now, for now we are doing the ingress, so it will be for the ingress interface, and then we get a reference to our eBPF program, and it is loaded into the kernel. So it attaches the process over here into the ingress mode. So this is the whole sequence of how we are loading a kernel and attaching it to the network interface. After that, you see what is happening over here is we call this a graceful shutdown. So here we are waiting for a async signal, that is via signal handling. So the program waits if we are pressing Control C without even blocking or polling our other executions. So this is the user space, but here we have the build.rs. The build.rs is actually where whole cross compilation is happening. So over here, it finds a eBPF package in the workspace. Then it cross compiles it to the eBPF bytecode using the IR build. And then it places the output where our user space program can find it. So this is the complete workspaces and the eBPF folder structures that we have defined. How to build and run the code. Now that we've understood the whole workspace, now we'll see how we build a project. So to build the project, first we need to go into our eBPF kernel space. That is your eBPF. Over here, we are going to do a cargo build. That will be for cargo. We are going to tell that you build it in the nightly toolchain in the release, and the target will be your eBPF EL unknown none hyphen Z build standard core. So what we say by this? So over here, when you say cargo nightly build, is that it tells that Rust to use the nightly toolchain, which is the cutting edge features which are not available in the stable platform, because eBPF, all the requirements and all are supported into the nightly tool chain. Then we say that target is your BPF EL unknown none. So this tells that BPF EL means the little Indian we are using. The Indian is little. So the eBPF bytecode format will be of a little Indian, and the unknown is going to tell you that it's a no specific. We don't have any specific vendor, and none. It means that we are not using any operating system. This is a bare metal program for the kernel context. So this will create a kernel code that can be executed. And the hyphen Z build standard core is where the hyphen Z is will tell you that it's an unstable Rust feature flag, and the build standard core is build only a Rust core library from the source. It will not build all the standard libraries that are used for your heap or file heap allocation, the file systems, or no networking API. So this basically we will build this. So over here, our kernel space is being built at this moment. So over here, while it is getting built, what is happening is that our source.main.rs, that is this, is converted into an eBPF bytecode, and then it will be generated in your target. We will have in the target folder, we would be having our what you say in the yeah, it's yet being built. So in the target folder, we would be having our kernel code. So the eBPF networking kernel code. So this is our kernel space has been compiled. We will just clear this, and we will go to our user space. Uh, we do a cargo build for the user space. So while this user space is being built, Here what is happening, that your normal Rust binary that runs as a regular program is being built. This has access to all your standard libraries, because if that is your file system and networking, as we are this is not responsible for the kernel space, this will load the eBPF program from the target folder into the kernel, and it will handle all the communication with the eBPF program, and the user space is responsible for alerting all your process alert in this thing, any alerts or events. So the kernel space is being, it does take its own sweet time to compile. Yeah. So the compilation has completed. We can clear, and now we can run the code. So to run the code, we have this the command that is sudo rust log info. We are giving the where our kernel probe, and we are saying to which interface we want to attach. So why do we require sudo? Because loading the BPF program into the kernel space need privilege access. So kernel modification requires all the elevated permissions. The Rust log info, as you can see, it's an environment variable for Rust logging. So we have set all the log informations. We can see whichever the alerts and all are there. So this is controlled by your user space. Then the target release folder is your compiled user space binary in the release folder, and the interface specifies the network interface to monitor. So now here we have been doing the ENP0S3. So let's yeah, here when we trigger the HTTPS of the GitHub page, logs have been coming from the port that is 10.171.234.30. But here you will be seeing that the unique ports has like 12 instead of just one. So the reason for this is, and there are multiple attempts. So the reason for this over here is that the GitHub page, which we are trying to connect, is not just making a single HTTP request, but instead it makes a request to many of the different servers, like for the port 80 on the HTTP, 443 HTTPS, the protocol is on 9148, and the port 22 for the SSH. So the modern websites like GitHub and all, they load content from multiple sources. That is why there are multiple what do you say ports connected simultaneously, and for a demonstration purpose we had kept this port limit threshold up for 10. That is why it has triggered over here. And another thing that we say over here is that the attempts we have are the multiple attempts. So for the multiple attempts, again, when we have each web page can trigger multiple attempts. So this is because they are trying to connect at different servers over here. So this is the complete say port scan environment. So here I would like to end over here by saying what is actually happening is that our user space program, it starts, it loads the eBPF code from the embedded binary that we have generated, the kernel code. The kernel loading is done when the eBPF verifier checks if the program is safe safe with all the rules that we checked, it has to say, and the JIT compiler converts it to a native machine code. And then once it is attached, network attachment is done, the eBPF program is attached to the ENS interface, and now all the intercepts. So we can see from the at the runtime operation, the eBPF program, everything happening in the kernel side, and it is being viewed in the user space. So to sum up with all the things that we've done today in this video is that we've seen the key features that Rust has showed. That is zero cost abstraction, where we had the high level Rust compiler that compiles an efficient kernel code. And then we have your memory safety without the garbage collection. That was the perfect for our kernel programming. Then we have pattern matching, which gives you a clean protocol handling the trade system, which we seen with the PODS trade for self serialization. The async can await in our user place. User program helped us for modern concurrent programming, and the macros we used for automated code generation. The cross compiler, which is compilation which we did in the build.rs, gave us a single code base targeting the kernel and the user space. And this is the last and not the least is our unsafe block, which gives us the power to do memory accesses, but at our own risk. So explicit boundaries where we take our own responsibilities. And the big picture, what we seen over here is that what we built is a sophisticated network security tool using modern Rust practices. That is your eBPF maps, which provided a shared state between the kernel and the user space. So the data transmission from the kernel and user space was smooth. Time window analysis to detect your scanning patterns, zero copy pasting passing. That was for the during the CTX load we seen that maximizes the performance. The LRU evictions, which prevent memory exhaustion, that is your least recently used hash maps we will have, and the async user space that gave us the what do you say we, the uninterruptible management of the event handling, and type safe serialization, which did not prevent any data corruption bugs, which prevented the data corruption bugs. Thank you.